In the last class we did DC motors, ठीक है. अच्छा, इसमें आपने एक बात रियलाइज करनी है कि लेट्स से मेरे पास एक वायर है, ठीक है. वायर को मैं ऊपर की तरफ अगर मूव कर रहा हूं, राइट. अगर मैं वायर को ऊपर की तरफ मूव कर रहा हूं, जैसे कि ये मोशन जो है ऊपर की तरफ पॉइंट आउट कर रहा है, right? When I'm moving the wire upwards, according to Fleming's left hand rule, where the first finger points from north to south, first finger, second finger is the motion of the wire, ठीक है. The thumb will point in the direction of the force, so the force acts downwards, ठीक है. Whereas this magnetic force or this induction will thereby lead to an induced current, right? Induced current की direction can be found out using Fleming's right hand rule. पूरा का पूरा right hand rule exactly the same as the left hand rule है. Just the fact that it is used to check out the direction of the induced current. So my first finger again points from north to south, ठीक है. My thumb points in the direction of the motion, and my second finger or the middle finger will point in the direction of the induced current, thereby telling me the direction of it, ठीक है. तो यही बात यहाँ लिख दी कि in the given diagram, when the wire labeled as AB, connected to a voltmeter is positioned in a magnetic field, induced EMF is 0. Either when the wire is stationary or it is moved parallel to the magnetic field, because magnetic field lines will never cut when the wire is moving parallel or it is stationary in the magnetic field. It should always be moving and should move perpendicular. However, if a wire is moved either upwards or downwards or both ways, then it will cut the magnetic field. Induction होगी, ठीक है, and thereby induce EMF is obtained. This induced EMF is given by the equation E is equal to BLV, right? This induced EMF gives rise to an induced current. The direction of this induced current can be worked out using Fleming's right hand rule. The first finger represents the direction of the magnetic field, the thumb represents the direction of motion, and the second finger represents the direction of the induced current. Fleming's right hand rule is used to work out the direction of the induced current. Right? Let's say I have a magnetic field strength of 80 millitesla. The length of the wire is 10 centimeter. Resistance is 2 ohms, and the speed of movement is 3 meters per second. Using magnetic force is equals to BIL, right? We can work out that the magnetic force that was exerted was around this value, right? The wire now behaves as a current carrying conductor placed in a magnetic field. It is therefore starts to experience a magnetic force, the direction of which is downwards based on the Fleming's left hand rule. This force opposes the actual motion of the wire, thereby confirming Lenz's law, right? मतलब कि जो induced current है, it will flow in a direction so as to oppose the motion of the wire जो हमने initially start off की थी. The magnitude of this magnetic force can be worked out using this calculation. E is equals to BLV. यहाँ से मेरे पास EMF value जो कि exert हो गए वो आ रही है, right? V is equals to IR or E is equals to IR EMF से I can work out the value of the induced current, right? And from that induced current, I can work out the value of the magnetic force. Basically, if this wire conductor is now replaced with a metal plate, the following arrangement is obtained. In this case, the metal plate is made to oscillate between two permanent magnets using point P as the pivot. So you can work out the fact that in this case, right, your if you use Fleming's left hand rule, right? Initially, if you use Fleming's left hand rule, your first finger points north to south, right? Your motion is in this direction, meaning to say your plate could move either in this direction or in this direction, right? About the point pivot because it's fixed, right? So for the case when it is moving in this direction, I'm using Fleming's left hand rule to work out the magnetic force, direction of the magnetic force. And I will realize that my thumb points in this direction. If you could check it out, right? Now that I have my magnetic force, I will apply Fleming's right hand rule. Right? And I will realize that according to this rule, my first finger points north to south, right? My thumb points in the direction of the motion, and my second finger will give me the value of or the direction of the induced current, which is downwards, right? Please understand that induced current will always oppose the change. Another name for induced current is eddy current. Now my question to you is, let's say you have V is equals to IR, right? Let's say for constant EMF induced, right? There's an induced current. If I want to decrease the content of induced current, because induced current is causing my plate to slow down, to decrease the induced current, don't you think if I were to somehow introduce some sort of resistance, it could decrease the value of induced current, right? So we use a technique called lamination. We will laminate the metal plate. How do we laminate a metal plate? We simply just cut off its cross-sectional area, right, such that this metal plate looks somewhat like this, like a comb, right? Now, laminating introduced air gaps. Air is an insulator, right? So doing this will actually reduce the content of induced current. So at one instant, when the metal plate is coming out of the page, the induced current, also referred to as eddy current, flows in a vertically downward direction. Because of this current, a magnetic force is established, which tends to push the metal plate into the page. Due to this opposing force, there's a damping or a loss of energy, thereby leading to a decrease in amplitude of the movement. The oscillation of the metal plate will stop after some time. If you want the oscillations to continue for a longer duration, the diagram shown in the following circuit can be used. In this case, the metal plate has been laminated. The term lamination refers to modifying the metal plate with the intention of either increasing the length or reducing the area. Both of these factors will contribute towards bringing about an increase in the resistance. Remember, from O levels, you know for a fact that resistance is directly proportional to the length of a conductor and inversely proportional to the area. So as a result, the magnetic magnitude of eddy currents will reduce, and lesser degree of opposition will now allow the metal plate to continue oscillating for a longer duration of time. So Fleming's left hand rule is used to work out the direction of magnetic force on a current carrying wire. The right hand grip rule work out the direction of induced current in a coil, in a circular coil basically. Work out the current direction in a circular coil. Fleming's right hand rule is used to work out the direction of induced current or eddy current. Let's say I have a magnet, right? And there's a plastic tube, right? There's another magnet on the right hand side with a copper tube, or could be any metal as a matter of fact, right? If I were to, they're asking you explain why the time of falling of B is greater as compared to time of falling of A. Now you need to understand that as the magnet moves through the copper tube or any metal, a change in magnetic flux would induce an EMF in the tube, because metals are conductors, right? Magnet has its magnetic field lines, and these conductors would cut those field lines. This induced EMF will give rise to the flow of eddy current in the tube. Eddy currents will try to oppose the movement of the magnet, right? Based on Lenz's law, the induced current or eddy current will oppose the motion of the magnet, causing its acceleration to become less than G. In case of plastic tube, current is not induced, therefore no opposition, hence acceleration of the magnet is equal to G and will therefore take less time to fall down the tube. According to Faraday's law, the rate of change of magnetic flux, right, will induce an EMF. The blue part highlighted is the Faraday's law. However, according to this induced EMF, there is a current in the coil generated that would oppose the change causing it. So the green part is basically the Lenz's law, the statement of the Lenz's law. So Lenz's law states that induced current opposes the change causing it. So if I were given a graph of phi against time, you need to understand that if they had asked you a graph of EMF against time, the fact that this is a sine wave, if you differentiate the magnetic flux, or if you differentiate the sine wave, you get a cosine wave, right? And the negative sign in the formula will reflect the entire thing like this. So you can now cut off the blue part. Similarly, you need to understand one thing, that you are provided, let's say you have a formula, phi is equals to NBA. Now, phi is the cutting or effect or the magnetic flux. Magnetic field strength B and phi are directly proportional. So therefore, if you were given magnetic field strengths graph and you were asked to draw the graph for phi against time, the shape is exactly the same. Values may change, but the shape would not. However, if you were asked to draw E against time, the EMF is equals to, again, d phi upon dt, right? If you differentiate a constant value, it becomes 0, and hence there's a 0. Or you could say there is no change. If you calculate the change in here, let's say this was a value 5, this was time 0, this was time 1. So your final value is 5, right? Initial value is also 5, and the time change was 1 minus 0. Don't you think your value comes out to be 0? So your change is 0, and therefore this value becomes 0, right? This is a decreasing slope. If you calculate a change, that becomes a constant value. However, when multiplied by the negative in the formula, this becomes a positive constant. Similarly, this part is 0. This part is a positive change. However, a positive change in value, if you differentiate it, it becomes a constant. However, when multiplied with a negative value, this becomes a negative change. And that is how you plot the graphs. About alternating currents, सबसे पहला topic is the rectification. Rectification is the conversion of AC current, alternating current, into a direct current. How do you do that? A diode basically behaves as a rectifier. Now, before we move on, you need to understand that diode has a forward biased and a reverse bias condition. If I connect the positive pole of the battery, right, to the anode, this is the anode of the diode, this is the cathode of the diode. So if the positive is connected to the positive of the diode, it will allow current to pass through it, meaning to say it is in its forward biased condition. If the reverse process occurs, negative attached to a positive, then this condition is called a reverse bias. In this case, the diode does not allow the flow of current. Alternating currents have an advantage that for 1 minute of the cycle, this becomes positive and this is negative. And for the other minute of the cycle, this becomes positive and this becomes negative, right? So this will allow the current to pass through, thereby giving you a wave, right? जैसे ही the current, as soon as the current enters the negative pole, this AC supply will switch its poles. Now this becomes a positive. As it becomes a positive, it will start moving in this direction. Now that's a reverse bias condition, meaning to say the diode will not allow the current to pass through it, and therefore a zero line, meaning to say no current is detected. Then again, this becomes the positive and the current flows in this direction. Again, a wave comes in. Okay? Please understand one fact, that this is a 50% power loss, because from one part of the cycle, you are converting the voltage and the current, but for the next part of the cycle, you are unable to do so. So this is not a very convenient method. Power loss would simply mean that I am losing out on a lot of money. Okay? So we tend to move on to full wave rectification. In this part, again, an AC supply connected to the positive part, the green lines will allow the current to be noted, to be worked out using this diode. However, if you check the red part will be allowed by this diode, and D1 will not allow it. So as a result, the green gives you a wave like this, and the red gives you a wave like this. Therefore, this diagram, but you need to understand one thing. Right? You need to understand one thing, that the flow of current is opposing one another. And therefore, this diagram is wrong. And this way, our purpose of converting AC to DC is not achieved. Right? So we cannot use this method. We use a full wave rectification method using 4 diodes. Now in this case, you have a positive and a negative here, right? They before I move on, you need to understand one thing, that when the current is in opposite direction, when the currents are in opposite direction, the AC supply simply again becomes an AC supply. So that defeats the purpose of rectifying it or convert it into a DC supply, right? So we use a full rectification method, and in this method, if you notice this positive part, the black one keeps moving. The black one moves in this direction. It will go here. It won't take this path, right? It moves to this point. It will not go here. It will move here, and from here comes here, right? Then at this junction, it will take this path because it has to reach its negative pole. Similarly, for the purple part, the next part of the supply, it moves from here, keeps on moving, right? Goes here, and when it reaches here, it moves in this direction, then in this direction, and then in this direction. And from here, it goes on here to here, and then the negative pole of the battery. You need to understand one thing, that the direction in cycle were same, and therefore your AC supply, which was initially this part, got translated as this, which is what you called a rectification, right? Now you need to understand one thing, that if I am adding a bulb here, the bulb will keep on flickering. It is it switches on, it will be switched on and will close, then switch on, then close, and will keep on flickering until it fuses. Meaning to say it's out of order, right? So to negate this condition, to negate the flickering, what we do, we apply a capacitor. The capacitor will cause smoothing. Basically, when you are at 0 volts, the capacitor keeps on charging, and when you are discharging, the capacitor does not allow it to go down. In fact, the capacitor starts to discharge its voltage, because capacitor is an energy storing device. So it will then again charge a bit and then discharge the voltage until the next cycle, and this process continues. If I apply more capacitors in parallel, this line starts to become straight. And therefore, if you notice, if you rub off these solid lines, you will notice that this is approximately a straight line. And therefore, you can say you have successfully converted an AC supply into a DC supply using diodes and capacitors. So this is the whole point. If a bulb is placed, it starts to flicker on and off. To enable smooth and stop flickering, a capacitor can be positioned parallel to R as in the resistor. If multiple capacitors are placed in parallel, the graph will be altered as shown. But if in series, the capacitance decreases, right? So that defeats the purpose. So we do not use the series voltage or the series lining. Moving forward, a transformer. A transformer is basically an iron coil, right? From O levels, we know for a fact that there is a step-up transformer, there is a step-down transformer. We introduce a magnetic field at the primary coil. Right, we introduce a magnetic field at the primary coil and the transformer will induce it to the secondary coil. Right, so moving forward, a transformer is an AC device that is, it converts one alternating voltage value into another higher or lower alternating voltage value. What's the concept of a transformer? A changing current in the primary coil will produce a magnetic field in the primary coil. The field lines develop a flux linkage in the secondary coil. Based on Faraday's law, a change in flux induces an EMF. Why should the coil be wrapped in an iron core? For the case of iron, it is permeable to magnet. Basically, iron is a magnetic material. Therefore, it allows all the field lines originating from the primary coil to link with the secondary coil. It can actually transfer all the magnetic field lines. This greatly improves the working efficiency of the transformer and makes it close to 100%. Basically, all the field lines, if you use Fleming's right hand grip rule, when the current was flowing in this direction, your thumb points in the north direction, meaning to say a north is induced here. Right. This field lines always converge out from the north and they will start cutting the secondary coil. These field lines are all concentrated because of soft iron. Why must the iron core be in a continuous form? If the iron core is continuous, it allows maximum flux linkage between the primary and secondary coil.
सर आपकी आवाज clear नहीं.
All I'm saying is an iron core will allow maximum field lines to be concentrated because iron is a magnetic material. So if you were asked why must iron core be in a continuous form, it should be in a continuous form because it allows maximum flux linkage or maximum field lines to be cut through between the primary and the secondary coil. Why must the iron core be laminated? Now you need to understand that when there is a cutting effect, there is an induced EMF, and induced EMF leads to induced current, which will oppose the flow of it. So lamination will reduce the eddy currents or the induced currents. So the term lamination applies that there are air gaps left between the structure of the transformer. If this is a transformer, I will slice it through, leaving some air gaps in between. An example of a transformer is the PMT that you see around you. A pole mounted transformer is a PMT. So this increases the resistance, hence the flow of eddy currents is minimized. As a result, there are less heat losses due to reduced eddy currents. Therefore, efficiency of the transformer increases. The transformer will not work if the secondary circuit is right between two north poles. Therefore, to